Uh, Welcome all of the participants to this our session on risk changes and open source tool for multi-hazard risk assessment and decision making. And this session is also two of my colleague, Professor Kesven Weston from ITC and Asuk Dahal from ITC. They are also presenting. It's a joint presentation of three persons. And we'd also like to have your feedback on the tool. And you can see a QR code at the top right of this screen, where you can use that one to send your feedbacks. Also, we have posted a link in the web link in the chat box. You can also use that one for post your feedbacks. And this will be real-time feedbacks. We will be showing the results at the end of this session. Next slide. The partners, AIT, it is a Institute of International Perspective Institute focusing on engineering, environment, and management studies. And ITC is also dedicated for developing capacity, particularly less developed countries, and utilize geospatial solution to deal with national and global problems. And the common between these two institutes, they have large alumni network, particularly AIT in Asia, and ITC, they have large alumni all over the world, but a lot in Africa. Alumni are in leading position in different countries. And we also we focus on capacity development, and we also implement joint projects. So one of the joint projects you can see, it is called charim.net, which is we implemented in Belize, Dominica, St. Lucia, Grenada, and St. Vincent several years ago, 5 years ago. And it was also funded by World Bank. Next. So our joint work also now, currently we are doing a project, multi-hazard risk assessment in Tajikistan, where we have implemented hazard, vulnerability, and exposure data to calculate loss and risk. And while doing this project, we confronted a lot of limitations, particularly data. This Central Asia region is data poor region. Also, if there is a data, there is a lack of sharing, data sharing. Then as far as hazard is concerned, no intensity maps are available for all hazards. And also very limited historical data of past disaster or hazard events, and which is very crucial for like landslide. It's very, very important, this kind of data sets. However, we established a GeoNode to whatever data we have collected or processed. And this GeoNode, many of you know, this is a World Bank initiative, open source, and is a very good platform for data sharing. We have also put hazard as well as susceptibility maps in GeoNode. Also density of phenomena hazard per return period also we have put there. And in addition to these two projects, we have also particularly work in Vietnam. There's a city called Hue. Every year, at least 5-6 tropical cyclone hit that city. Very flood prone. So we work on a DB project there. Then also we have done a very excellent work here under World Bank in a project in India, in Uttarakhand, for flood, earthquake and landslides. It was also for the whole state of 56,000 square kilometer area. Next. So in the project in Tajikistan, you can see the risk profile. This website, the web link I have shown in the previous slide. If you go there, you can see the risk profile administrative unit, district, sub-district level, You can query hazard, exposure, loss, and risk data. Then challenges need to update data at local level, so which is very, very challenging. A risk assessment tool is required at local level. This is also in-house. This is not really available in most of the developing countries. Includes scenario analysis because climate change is coming. I mean, it's happening. So things are changing. So we need to have some future scenario for climate change. This is very important while doing risk assessment. Also include socioeconomic data and indicators for more robust or comprehensive addressing risk in more comprehensive way. So these challenges we probably will take in next stage of this project is the UNDP funded projects. We are discussing with them. Maybe we can address in the next stage. Next slide. So all these challenges or all this experience in different parts of the world, both the institution, we thought that there is a room for making some kind of software or tool which can be used by all the countries and make it open source as much as possible. So the first thing is non-available multi-hazard risk assessment tool at local level, which I have already mentioned. So this is a need. Often, whatever risk assessment tool available, they are quite complex, data intensive. So that's why we try to aim to solve these two issues, make it a little bit simpler way or more intuitive way, and data flexibility. If you have more data, you can use more data, but if you have not sufficient data, still you can use the model tool. And some of these risk assessment are country specific. For example, if you look at right-hand side, Jesus, which is a mostly US centric software, or if you say a RiskScape, which is mostly New Zealand, that area. Some of them require link with specific software and data. For example, if you use Jesus, maybe you need RGS, linked with RGS or some other tool. Then required software are not available or maintained, as maybe it is also challenging because some of these softwares, if it is not open source, it is maintenance or you have to pay a lot of money. That is also difficult in developing countries. No multi-hazard interaction and don't provide loss and risk information. So this is one challenge. Most of these tools many of these tools are single. For example, OpenQuake, which is earthquake centric. And also say INSF, which is developed for Indonesia, which is very good tool for exposure assessment, but not risk assessment in true sense. So these are some of the challenges we are trying to address using these RiskChanges. And also most of the tools does not include risk reduction alternatives. So we'll be trying to address those and also include future scenarios for climate change. So we'll have because of climate change, so many millimeter of rainfall going to increase, then how risk will be changed. That kind of things we will be trying to incorporate. And as I said, it will be, I finished my part here and I'll hand over to my colleague, Professor K. Weston from ITC. Professor K, so over to you.
Okay, thank you very much, Mansoor. In continuation, I would like to discuss a bit more about the specifications that we developed for this system. As we noticed, there's a need actually to have an open source tool that would be working in a cloud environment. So without clients having to be very knowledgeable about how to manage or analyze GIS data, but being able to do this within a cloud environment. Also in terms of a generic tool, which is not specifically focused on one type of hazards or one type of elements at risk or a specific scale. it would be able to, the users would be able to generate their own projects. So there is a component within the system where you could generate your project and where you could share the results of that project with people that you assign to the same project. And you would have a project manager. So it's actually, in that sense, within the cloud environment, you're working on within a selected group. It's looking at multi-hazards, and so it tries to address the interactions between hazardous processes as much as possible. We'll come to that a bit later. It will incorporate the component of loss estimation for specific scenarios of hazards and element at risk combinations, looking both at physical losses as well as population losses. It then aggregates the information in risk assessment using spatial units that the users also provide. They could be administrative units, for example. So the system could analyze the current risk. So that's where the basis is of the system. That's where it starts with. Based on that current risk evaluation, alternatives can be formulated for risk reduction, and say the effect of the risk reduction could be analyzed through the system, using also tools like cost-benefit analysis. And on top of that, also future trends in risk could be introduced. And so then also alternatives could be evaluated under future trends. The idea is that this tool should be used at the local level. So by, for example, medium-sized cities that have to make decisions on planning of parts of their city and where they have different alternatives to take into account. And so also by people that have, say, are not super experienced in hazard modeling or risk modeling, but should be able to use the system with the data that they have. It would be also using, for example, hazard data in cases where we have no hazard intensity maps, as would be normally the requirement in a lot of other models, where for certain types of hazards, this would be really difficult. And so it's possible to use susceptibility maps instead. And also the option is there to integrate expert opinion when the input data is not sufficient. So the system could be visualized with a number of individual components. First of all, there is the component that looks at the current risk. So the current risk takes, on the basis of the stakeholders within their legal framework and say their requirements, they would formulate a project on assessing the hazard, both either in terms of susceptibility or intensity frequency information, collect information on elements at risk, which could be also different, as we will see, whether it would be building footprints or land use based, analyze, use vulnerability assessment, using also a database of vulnerability curves that would be within the system, but where users could add their own vulnerability curves to it. Then perform the loss estimation and risk analysis within the system, and then go through a stage of risk evaluation where they would decide which areas need to be adapted, in which areas measures should be taken. That would mean that you would move to the next stage where we would where stakeholders introduce risk reduction alternatives. So packages of possible mitigation measures, be it structural, non-structural, combinations of those, which could be done, or also planning alternatives, so land use plans for certain regions, and they would like to evaluate what would be the effect of those on the hazard and the risk. And so they would introduce these plans and would look at the consequences of those in terms of exposure as well as hazards, reanalyze the risk, and do after that a comparison between these different alternatives using cost-benefit analysis and taking into account other indicators in multi-criteria evaluation. Another workflow within the system is the evaluation of the effect of future scenarios. So climate change, land use change, population or economic changes based on possible trends. The effect of those on hazards and on exposure are evaluated and are incorporated within the system in a risk assessment to see how much risk would change over time. And finally, we have, say, the combination of those is to implement the implementation of risk reduction alternatives under future scenarios. So the decision support system allows for all these different options to be considered by the stakeholders. So to illustrate this a bit, I'm showing here one example from how this was used in the city of Medellin in Colombia, where within one of the municipalities of this large city, municipality of Envigado, a study was carried out to analyze the, the change of risk in relation to multi-hazards, in this case, flooding and debris flows for future trends, as well as say what would be optimal risk reduction alternatives. So within a study like that, first multi-hazards would be analyzed for the present situation, where we used an open source multi-hazard physically based model called OpenLISEM Hazard, developed also by ITC, by our group. And this was used together with exposure information to quantify the present risk. Next, we look at future changes in terms of urban growth and climate change. And then we evaluate what would be the change in risk in future based on these formulated possible scenarios. And then a set of planning alternatives was formulated and see how these planning alternatives would behave under future scenarios. The city itself is very rapidly growing. It's a city constructed on an alluvial fan of a river, which has a significant hazard in terms of flooding and debris flows. Here, some examples. So we have the multi-hazard modeling component, where the multi-hazard model was done for debris flows and floods for different return periods. Elements at risk, in this case, the building stock was analyzed, was characterized in different types, and absolute vulnerability curves were developed that took into account, say, the effect of flooding and debris flows on buildings, including, for example, the effect on underground parking garage within an area like that. This was used in the risk quantification, where the combined hazard was evaluated in the individual hazards, and the average annual loss was estimated for that specific situation. Subsequently, future trends were analyzed, where a population growth scenario was evaluated, as well as a climate change scenario, where population change was looked at with a population growth rate, and also the additional requirement for space in terms of apartments was analyzed, and so based on the development plan of the city, which areas would be developed in future, and also densification of the city in making buildings taller. We looked at the effect of climate change in terms of the higher frequency of events using studies that had been carried out in Colombia on, say, the increase of expected frequency of rainfall events that could trigger these flash floods and debris flows. These were fed again into the model, and say hazard maps were reanalyzed back then for these different scenarios in future years, in this case 2050, and also vulnerability curves were generated for those situations. So then, as a result, say, in the two scenarios where we would have the increase of population results in a certain increase in overall risk, but if we also add the effect of climate change, yeah, the increase would be much higher. Then also risk reduction alternatives were evaluated. So looking at the adaptation in terms of hazards, so channel deepening or sediment retention basins were analyzed in relation also to the future scenarios, giving a very limited amount of benefit at the end, whereas, say, adaptations in the vulnerability part, for example, flood proofing of buildings, turned out to be a much higher effect under these changing scenarios. So it is an illustration of how such a system can be used in deciding which options for risk reduction would be better in a particular situation. In order to analyze this, we are developing a model, the tool that has a number of different components. It has a series of technical components and decision support components. So the technical components deal with the inputting of the data, and there we are putting a lot of emphasis also on what is the normal availability of such type of data in a typical city. So without being too restrictive on what type of data could be entered, of course, it will have also its implications if there are, for example, no element at risk data with characterization of the elements at risk. It would be difficult to assign vulnerability curves to that. But this is, say, taken into account within the system. So loss estimation components are done, so where the loss for a specific hazard and specific return period is analyzed, combined within the risk analysis, where we would also look at the hazard interactions and what the hazard interactions would mean for combining the different types of losses. We have a cost-benefit analysis, which calculates, say, what would be indicators like net present value for specific alternatives that we define. And so in the decision support part, we have the definition of alternatives and then the translation of these into the input data needed for the model, as well as definition of scenarios in future years that would also lead back to the input. The multi-criteria part at the end is the part where we take the results of the risk analysis of the cost benefit together with other indicators in deciding what would, in helping decision makers to decide what are the best options. Within a project like this, there are many people involved. So the experts coming from different directions. And so we are also having a system where developing the system so that different stakeholders can upload their type of information into a common database using this project approach, and where you define roles between the different actors. Some things about the input in terms of hazard maps. Typically, hazard maps would be multi-hazard maps showing different types of hazards. Here, an example of the demo data set that we are using, where you would have debris flows, flash floods, tsunami. They would each have its own type of intensity measure. And so it's not specific for an intensity measure. You could put any intensity measure there. And the idea is to put in information for different return periods. So intensity for different return periods, but a number of hazards will not allow you to do that because you cannot represent the data as intensities, or there is only a susceptibility map available with high, moderate, and low classification. In such cases, we integrate that the user is able to decide, okay, within the classes of the susceptibility with different events that have a higher or lower frequency, what would be the density of the area affected? This could come from historical records in case of landslides, or partly also from expert judgment. So a what if part. Then we look at hazard interactions. So taking into account what could be the possible interaction between the hazards. And they would very much depend also on the way how the losses would be integrated, would be combined, whether maximum losses would be taken, whether these could be added up, or whether we would say look at the maximum in sequence as well. The elements at risk part allows you to put in elements at risk types that are either points, could be specific objects, linear networks, transportation, building footprints, land parcels, or grids. The system also has its own vulnerability curve database, so where you can query the database with respect to the items indicated here. And so where you can find which vulnerability curve would represent best the situation in my area. Users can upload their own vulnerability curves using simple CSV data sets and can visualize, and later can link vulnerability with the type of elements at risk. So that could be both done in building footprint level or in land parcel level or linear transportation networks. So different options are there. So the system workflow is that we go through data input of these different types of maps stored in the database. It's important to mention the data can be locally uploaded or can be linked to GeoNodes, for example, or other web-based services. We do the exposure analysis, then goes through the loss analysis and the risk analysis, and eventually the cost-benefit analysis. So some of the features of the system, it supports data import from OGC services, as I mentioned, GeoNodes, manual uploading, multi-user and multi-organization, so organized into different projects. Will support fast computation using multiple servers, has a graphical and map-based visualization, and it will run on different devices. It's web-based, so it's not specifically designed for a certain device. So these are a number of the key aspects of the system. The system is in development, so we are not yet at the stage where we can show a full-fledged demonstration, but we have nevertheless started this this session also to get feedback from you as an audience, experts in risk, and also planners through the questionnaire that we have, where we sent the link to. Next, my colleague Ashok will demonstrate some of the components of the system. Ashok, to you.
Thank you, Professor Kes, and hello, everyone. Thank you for letting me speak here. I'll just go briefly. The system is still work in progress. It's not full-fledged, as Professor Kes told. So I'll start with the few things. I'll show how the system works. So next, the basic structure of the system looks like this. It's open source system, and all the components that are used in the system are open source. So database, we have the PostgreSQL database, and the user can access the system through cloud or the internet, simply saying. And then we have most important libraries, like the RiskChanges library. It's a Python library which is behind the graphical user interface, which does all the calculations. So you can also install this library using the Python user library installation procedure. And also we have GeoServer REST library. Then based on those different components, we have the graphical user interface built on Django and React. And this is the core part of the system. So next, the system components that we have are like it's just the same diagram but in a different way. We have the graphical user interface, then data management module, vulnerability database, which is a another part of the system which have a vulnerability for different reasons, and it is also public, so anyone can access those vulnerability database. And in the computation module, we have four different modules. I'll go through each module and try to show some screenshots of the current system, but I'll not go through all the screenshots, but I'll tell you more about how the computation is done. So the main interface looks like this, and if you don't have an account, you can register. But how does it work is you cannot register as an individual person. It should be an organization. So when you register, you get an organizational username and password, which is the administrator, and then they can create multiple users and multiple projects. So each user is linked to one or many projects, and they have the access to only the data and computation related to their projects. So it's more of a project-based system. And in the beginning, you can see the freely available data or the model, but you cannot see, you cannot upload or do most of the calculations. Then when you log in, you can select your projects using this drop-down. So I'm now logged into the Tajikistan loss calculation, but you can do any project that you want, and this will be your username. Then we have four different sections: data management, modeling, planning, and decision making. So in the data management section, you can upload the data such as the element at risk, vulnerability, hazard, and many other things. So in the element at risk, you can upload file, or you can link to the GeoNode using the Open Geospatial Consortium services, or you can directly link with the database that you have in your server. And then you have to give certain metadata. Let's say for the element at risk, you have to define uh, name of the layer, then type, which type of the element at risk it is, and which risk reduction alternative does it represent, and what is the year of representation, and what is the future scenario. So this is for the element at risk. And for the hazard, we also have same other things, but in hazard, the system also have a feature to have, like, let's say for the return period, we can have average, minimum, and maximum. So in modeling the hazard, it's not exactly the same return period always, but we also have some, how to say, the discrepancies or some uncertainties in the data. So the system can also recognize those uncertainties and do the calculation based on those things. So next, the vulnerability. This is a bit more interesting. So when you have a project, you can either create your vulnerability curves public, because in most of the world, even though we have the maps and we have the hazard models, we don't have a proper vulnerability curves. So this is the free and open system. So uh, most of the other data are secured and private, but if you have a vulnerability curve and if you would like to share with other users, it is going to be public. So other users can also access the vulnerability curves. If there is a similar project by different organization in similar locations, then they can use the vulnerability curve from other projects or other organizations as well. So next is alternative and scenario. So we can define the alternative and scenario and their cost and their project related files, but these are like just management of the folders, but the data will be mostly element at risk, hazard, and vulnerability. Then after we have done the data management, or we have uploaded the data, then we can do exposure analysis. In the exposure analysis, we have three different steps, which is hazard and element at risk selection, then visualization, then aggregation. So you can do the combination using this kind of window, which helps is like, if you have, let's say, three different return period for two hazards, which is 6 hazard layers, and then 3 element at risk, then it will be like 3 multiplied by 3, it's a exponentially growing number of combinations. So to reduce user from having to click multiple times to do the combination, it processes on batch. So you select a particular hazard and particular element at risk, let's say building and the flood, then it will create all the possible combination of building and particular flood and do the computation. So it might take half an hour, then it will notify you that the computation is complete. So you do not have to repeat the same process again and again. And then the results will look like this. This is a dummy map. So this is an example from Huawei, where the exposure map will look like this, and the information will look like a bar chart or in a graph, you can see that. And then after we come to the point of loss analysis. So I'm not going to now show the screenshot, but I'm going to talk more about how the system computes the loss, instead of saying like, oh, it computes the loss, but how. So here it takes the exposure data as input. So we have different hazard intensity map, different element at risk maps. As I told before, it creates the combination, let's say for the flood and building or land parcel. So it creates the different combinations and then do the spatial overlay, the spatial analysis to calculate the exposure. Then it will divide the units. So dividing the unit means like if you have a big land parcel and if you have a flooding in the half of it and there is no flooding in the half of remaining part, and if you calculate considering it as a 1, then you will extrapolate the information, or you will overestimate the loss. So it will divide which part of the building or which part of the road or which part of the land parcel is flooded with which kind of hazard, like which intensity of the hazard. And based on those intensity of the hazard, let's say for the flood 1 to 10 centimeter, then it will look up the vulnerability tables. And one good thing with the system is when you give vulnerability data as a point, like for this much of hazard, this much is the damage, it will do the polynomial fitting using some equation. It will basically create a vulnerability equation from the data that you give as an input and identify the better vulnerability, which is a bit better than using the points itself, because vulnerability is never like a linear process. And then it multiplies the cost or the value information with the vulnerability information, and then aggregate per the unit that we divided in the second step, and then again aggregate per the administrative unit, which is aggregation per, let's say, the municipality or the wards or whatever the administrative unit it is. Then after we have loss for different scenarios, we can do the risk analysis. And for the risk, let me give you a basic example. Like if you have a the flood and debris flow at the same time, and it happens at the same location, then if your house is already destroyed by the flood, it cannot be destroyed using the debris flow. So what the system does is you can group the different hazard and give the weights. So if you group the flood and debris flow as one group and landslide is another group, then it will determine the hazard dependence, and then it takes the maximum loss per unit group. So if the loss from flood is maximum, we take the flood, or from the debris flow is maximum, we take the debris flow, and then sum up all the losses per unit and then calculate the average annual loss, which is risk. And this can be done as a element at risk level or at the administrative unit level. And for example, this will be a basic example like flood depth for different return period in the city of Hue in Vietnam. So this is the flood map, then this is the element at risk map. When we do the overlay, it looks like this, and the risk looks like this as a administrative unit aggregation. So this is a sample. And now we have done for a single case where we have a hazard, we have a element at risk, and we have vulnerability, and we calculate for the current scenario. But there are also different alternatives, risk reduction alternatives, such as engineering solution, ecological solution, and relocation. So in each alternatives, it will either change hazard or element at risk. So if you see in engineering solution, it mostly changes the hazard, but very less, partly in the element at risk. And in ecological, it's also the same, but in relocation, it does not change any hazard, but mostly the element at risk. So whatever is changed by your alternative, risk reduction alternative, you have to upload that data same again to the system and do the same calculation that I explained before. So now we have for different alternatives, you can see how the different risk is there. And after we have the different risk values for different alternatives, and also we have the cost related to those alternatives. So after having those costs and how much the improvement is done or how much the risk is reduced, then we can do the cost benefit analysis using different economic indicators such as cost benefit ratio, net present value, or other things. So this is how it does it. We have the user interface, we give the inputs, and then it calculates for average annual loss for multiple scenarios and cost and return information for alternative planning, and then we do the ranking of the alternatives. So then multi-criteria analysis is also, you give different input and we give the different weight for those input values. It is mostly useful for not the physical element at risk, but like social cases. Like if you have different people vulnerable to different things, then you can do the multi-criteria analysis. Also, you can do for the cost reduction, risk reduction alternatives, you can do the multi-criteria analysis. And now we have done up to like single hazard, single risk assessment, then with the different alternatives. But we also can consider the future scenarios using the system, such as business as usual, where the climate change is very limited, but the rapid growth without knowing the risk, and then risk informed planning, where we know the risk, and then the limited level of climate change is there. Worst case is like severe climate change and rapid growth without taking into account the risk. And like you can create a different scenarios based on your needs, and you can see how the risk is in each scenario. So after you have many possible future scenarios, you know the risk on which scenario, how does it look like. And based on those information, what you can do is you can see how the risk will change by using which alternatives in which scenario. Thus, the name of the system is RiskChanges, because it will allow you to help in decision making by looking at the different risk reduction alternatives, different future possible scenarios, and different alternatives to to understand how the risks will change in different different decisions or different planning alternatives. So the system name is itself RiskChanges. Thank you. I think that's all from my side, and you can go to the form that we have to give your feedback, or we have some questionnaire. And still the system is on development, so if you want to do some programming, or you want to help us to develop the system more better, or if you have certain ideas, you can also contact us, and there is the form where you can give your email address so that we can contact you for the further collaborations. Thank you. So back to the Dr. Mansoor.
Yeah.
Yeah.
So Mansoor, back to you. Mansoor.
He's muted, I think.
Are you muted, Mansoor?
Yes.
Okay, sorry. So thank you, Kees and Ashok. I think we have around 12 minutes for question and answer session. There are some questions in the chat box. Some of them are privately, some of them are in public. So I will ask the important ones. Maybe yes, one question is from Mr. Koji Suzuki of ADRC. He says, in case of Colombia, how did you localize or downscale the climate change impact for a particular area? How do you distribute the buildings, a variety of buildings for the future?
Okay, this is in Colombia, we used the information from, say, the National Meteorological Agency that had done this work, that had looked at intensity, duration, frequency curves, and how, based on climate downscaling models for different parts of the country, how these would change over time. So we didn't do that type of work, and I think it's also probably relevant to indicate that the stakeholders that would be using this system would generally not be able to assess that. So they would need to have information from others, say from the national agencies, for example, on the meteorological agencies, to give them feedback on what would be the expected changes following certain future climate scenarios in a particular future year. And this could be as simple as saying, we have now return periods of frequencies of hydrometeorological hazards that are like this, but with the same intensities. But how much would the frequency of such intensity events change? So you would have say a 50-year return period flood event. That same type of event, how more frequent would that happen in future? And I think for that local decision making, such type of information would be generally better than to request a full downscaling of climate models, because that would require a lot of additional work, where this would be very difficult to do for many of the local administrative units that would apply this. But they would use it what if the climate scenario becomes so that we have an increase in intensity of in frequency that would be so much, say 20% related to as compared to now, how would that change my risk? And so it does not necessarily require to reanalyze the hazards, but could also be looking at, say, just adjusting frequencies. And so the system itself does not do the hazard modeling. I think that's also very important, because that requires a lot of additional input data and knowledge. And so it assumes that hazard data is available, or that could be obtained through others. And so also for when we're looking at different risk reduction alternatives, the translation of those plans into how hazard would change and how elements at risk would change goes prior to feeding that into the system.
Okay, thank you, Kees. So there are some few questions. Just let me, one from Marianne. Thanks, interesting tool. Will it be developed such that you can choose only to perform certain elements of the analysis? No. And question 2, will you allow multiple file formats to be submitted? Maybe
yes.
Yes, maybe I think you can.
Well, maybe first, I think multiple file formats.
Yes.
Yeah, sure.
Maybe I can say about that. Yes, it is based on the open source library called GDAL. So most of the supported file formats that are supported by the geospatial community will be supported. And also for the analysis, I think yes, up to, like, if you go from exposure analysis or loss analysis, it is possible. But if you want to do the cost benefit analysis without doing the risk assessment or exposure analysis, that might not be possible. But in a certain extent, yes, it will also be able to do the certain elements of the analysis.
Yeah, so it is indeed also possible to select only exposure analysis. So if the data does not allow you to go further towards loss estimation because you cannot represent intensity or you don't have vulnerability information, you could do an analysis also just based on exposure. But of course, the system can allows you to also to integrate it with simple steps, for example, using simple vulnerability curves, or say entering susceptibility maps with estimated spatial probabilities for different events to go one step further, say, without having to reanalyze the data. So you could do definitely individual components.
Okay. So there is one question from Ajay. I understand that the loss quantum is assumed on basis of damages to physical infrastructure only. Will the tool have function to assess the business income losses? The cost-benefit analysis could be impacted substantially if losses on business income is factored in. Yes, I think this is true because which we call opportunity cost. So if you lose business, there will be a lot of reduction in the income itself. But at this point of time, I think we are looking at the physical damage only, but that could be considered maybe later. But Case, any comments on this?
Yeah, I think the system now looks at direct physical damage. Yeah. And so the information from the direct physical damage feeds into your cost benefit analysis, where you can then, based on the direct physical damage, also add indirect damage, but the system itself is not designed yet to do that.
Yeah. So one question from Ricardo from NASA. How many people do you think is needed in a team to dedicated to this task? I think we have 5 people this time we are working. Out of 5, 2 people are very much dedicated. I mean, almost every day they are working. We other 3 also advising and guiding them. There is one questions more, maybe, okay. This is from Javed.
Maybe also, Mansoul, in relation to the end user, so the team of the people that would use the system that we preview is that you would have to have, say, you work together with different organizations. So you would have to typically in a municipality with a person that is able to manage GIS data. So who would be the one, say, managing the technical input, but the data itself would come from other agencies that would be specifically doing the hazard assessment. And so they would upload the hazard data on the system so that the person at the central organization can use that subsequently. So you would need a person for hazard assessments. Depending on the hazard types, they would be definitely different people. And elements at risk would also generally be another organization. And then, of course, the technical person, say, managing the system. And I think decision makers are more coming in when you are dealing with the multi-criteria evaluation part and the results of the cost-benefit analysis.
Yeah, thank you. There are a few short questions. Let me answer quickly. When it is expected to have the first demo or beta version for us to try, test, implement in own cases? I would say maybe mid next year, 2021, mid.
Yes.
That will be more realistic.
Yep.
Another question from Hamid. What is your suggestion for some countries with data limited, such as Iran? I think we have already said Tajikistan is near next to Iran, and they are also similar situation. We have in this data poor situation we have implemented. I think our system will be flexible enough to have data poor situation or data rich situation. I think one last question, this is important question, Case, I think I'll direct to you, is from Javed Ali. How do you consider hazard interaction in multi-hazard risk assessment? Also, have you taken dynamic vulnerability into account for risk assessment?
I mean, it's not directly in the system, but you can use the system to do so, because that would mean dynamic risk assessment means that your vulnerability would actually change after the impact of one hazard, sorry. And so the system allows you to upload different vulnerability data that you would use in sequence. So my answer, you can apply that, but it's, I mean, in practice is very not frequently done, but to estimate how the vulnerability changes after the impact of one hazard event is still a very a research topic, and there are very few, say, operational vulnerability curves that could be used for that.
Yeah, I think that ends our session. It's exactly on time. I think I'd like to thank all of you for all the participants, and we'll expect your feedbacks, and you can reach us. A great thank to all of my colleagues for doing this session. Also, thanks to World Bank people. I think with that, we will finish our session here. Thank you very much.
Thank you very much. Thank you for attending. Goodbye.
Goodbye.